What happened with this? Sorry. My keyboard does not work. Okay. Maybe it's just slow. Okay, this is the table of content today. First, let's review some basic terms related to the microstructure. Then I will introduce you some investigation methods and as well as the definition and representation of microstructure of the crystallographic orientation. Change this one. Where's my mouse? I think I would like to restart it. This looks strange. Okay, sorry. Okay, this time looks better now. Okay, then I will introduce you some investigation experimental techniques and also the definition of crystal orientation and representation of grain size and shape. Then in the second part, we will learn software used for the microstructure characterization. And if we still have time, we will go for the tasks in the assignment. And also, if you have questions, I will try to answer it. And before we start, please make sure again that you have already downloaded and extracted the MATLAB Mtex toolbox and copy it to your MATLAB work folder. And also please download this EBSD date file and we will use it as input later. You can find the steps for this slides and the lecture slides are already uploaded to my courses material session. So you can find how to do it in that slides. And now we will start with the microstructure characterization. So the first question is, what is microstructure? Okay, one question. Jamie, did we need to record this session? Okay, you are already recording.
I did.
Yeah. So let's back to this one. What is microstructure? There is a code road shape still, and if you zoom in the this part, use some microscopes, then you will see a microstructure like this. So microstructure is an arrangement of the constituents of a material. It describes the spatial distribution of elements, faces, orientations, and defects, and so on. Then what is faces? Face is okay. Face is a region of a material that shows the uniform mechanical composition and structure. In one phase, it normally shows a similar physical and mechanical properties. And what is grain? So grain is a region that shows a uniform orientation. In a single crystal, there is normally only one grain with one orientation. But in polycrystals, there is it always composite of many different grains. Then next question will be how we can observe this kind of microstructure. The basic answer is by the microscopy. So the most simple one is this light optical microscopy, LOM. So with a LOM, it usually has a magnification up to 2,000 times with the resolution larger than 0.3 micrometer. If you want to observe your sample under a LOM, you need to prepare it first. First is mechanical grinding and polishing to remove the surface filters. Then you need to do the chemical action for the sample because the chemical, if you have the different phases or grains in your material, they will have a different chemical composition or the crystal orientations. Then after after action, it will show a different reaction with your chemical solution. So you will see a different surface roughness condition. Then the refraction of the light can be changed. Then on your LOM image, you will see a different colors of these black or white regions responsible for different phases of grains. One more important thing is about the grain boundaries. So if you have a polished and etched surface. As we already learned during lecture session, the grain boundary is a defect zone. That means there is more space for elements. So the grain boundary zone is where the element prefer to segregate it. So it is more sensitive to chemical action. Therefore, after action, the grain boundary surface is normally lower than the within grain zone. So under your LOM, these black lines will show as the grain boundaries. And for this LOM technical, we can see that it only shows a roughly presentation of grains and faces. It will give you more information about grain orientation. So we will need more powerful microscopies like the electron microscopy. The basic idea of the electron microscopy is based on the reaction and interaction of electron beams and a solid. For example, this is our solid samples. And if you have a incident element beams, when it encountering the solid at this point, it will generate a huge amount of energy. Then you will, they will active some refraction signals. For example, we will have first the secondary electrons. It will generate within a small range close to the surface up to 100 nanometer. Then we will have this backscattered electrons. The range of it will up to 2.5 micrometer. Followed, we will have this characteristic and decelerated X-ray signals. This range is a little larger, up to several micrometers. Then we can design different kinds of detectors to receive and analyze these signals. For example, for SEM, the scanning electron microscopy, there are three most important signals and for detectors. The first one is the secondary electron signal. It will received by the secondary electron detector, SE detector. So as we already said, the secondary electron always generated close to the surface within a really small range. So it is really sensitive to your surface roughness or surface morphology. Therefore, the SE detector is normally used to observe the surface topography. Then it's the bank-scattered electron. It is always received by this BSE or EBSD detector. This signal is quite sensitive to your crystal orientation and crystal structure. Therefore, it is normally used to analyze your crystal orientation. Then is the X-ray signal. Here in SEM, there are two kinds of detector can receive this X-ray signal. It's energy diffraction X-ray detector or the wave diffraction ones. So the X-ray detector or the X-ray signal is sensitive to your elements. So that responds for different chemical composition. You will observe your local chemical compositions by these two detectors. Furthermore, if we have a larger enough incident energy, and also we have the reduced surface, the thickness of the sample, then we will have this kind of transmitted electron. It is used for TM, the transmission electron microscopy. TM will have a finer solution. Therefore, it is normally used to observe an inner microstructure topography in a much lower or smaller scale, like for lattice dislocations, grain boundary or sub-grain boundaries. So we will have a more detailed look for this EBSD detector. As I said, if you have a incident electron beams, it will encountering your sample at this method point. Then it will generate many bank-scattered electrons. They will be received by this detector, and they will show a diffraction patterns like this. This is an example for the diffraction pattern. This pattern is named as the K-Cushion pattern. It is sensitive to your crystal structure and orientation. If you have another grain or another crystal, the shape and number of this Kiku chain pattern here will be changed. Also, the width of this line will also be changed. Here, this refraction lines is responsible for the crystal orientation plan. So, for example, it can be indexed like this. If you have this kind of Kiku chain pattern, you can compare it to your standard database. Then the detector can figure out which kind of crystal plan it is. Then it will give you a conclusion on which kind of crystal orientation on this point. I will explain you about the crystal orientation later. So this process or this program is named as the index during EBSD measurement. And if you do the measurement point by point in your observation or investigation area, for each point, you will get one grain orientation. Then you will get an orientation map like this. So this colors here is responsible for the orientation color coding. So to sum up, this is a symmetrical join for your investigation system. If you have a source, no matter it is a light or electron beam or ion beam or X-ray, and you can have this source interaction with your samples. It will active different kind of signals. We will have a special detector for these signals to receive them and analyze them. Then you will see this kind of images like here, or only some values for XRDs. And these images will help you to observe this the microstructure of the material. For example, for LOM and SEM, you will see the basic information for phases and grains. And for EBSD, you will do a detailed analysis about your grain orientation and also size and shape. We will explain it in detail later. And for EDX, you can see your chemical composition distribution. This is for titanium. And we can also see that this titanium is also it's always segregation along these grain boundaries. And for TEM, you can see like this dislocation lines and also here grain boundaries. And this is micro-CT. This application for micro-CT is used to observe this voice. It's marked in red area. And also we can have APT. You can see this technician have a quite finer less scalar, so it can observe your local chemical composition distribution. Actually, this kinds of advanced techniques is not only used in material science and engineering. This powerful techniques is used can help us to observe the micro world. So it will be used in many fields in science and engineering. I think today you will only see the first image of them, and you will be familiar with them in the future. As we have already talked or mentioned several times, what is the crystal or crystallographic orientation. So what is really the crystal orientation? Here we should notice that in materials, there are two levels of coordinator definition. The first level is this kind of external coordinator or external axis. This is named as material coordinator or sample coordinator. These coordinators are related to your production process. For example, for this cold rolled sheet, you will have this rolling direction and the normal direction and transfer direction to combine as the sample coordinator. And for the AM materials, you will have this building direction, scanning direction, and transfer direction. And then in the microscopic level, you will have this crystal coordinator. And this is related to your crystal structure. So here, this is an example for a cube, like a BCC or CC or simple cube. So you will have these three kinds of axes to combine as a crystal coordinator. Therefore, the crystal orientation is defined as the relationship between your sample coordinator and your crystal coordinator. In mathematical way, it is defined as this rotation matrix to transfer the sample frame or coordinator S into the crystal frame C. So this orientation, this rotation matrix is 3 times 3 rotation matrix. It have a mathematical definition in this way. Here, the alpha 1, beta 1, gamma 1 is the rotation angle between the crystal axis 1, 0, 0 and the 3 sample axes, the x, y, and z. For closed root sample, they are RD, TD, and ND. Then the alpha 2, beta 2, gamma 2 is the angle between this crystal axis y, the 0, 1, 0, and these 3 sample coordinators. So the same it's the same for alpha 3, beta 3, and gamma 3. It's the angle between this 0, 0, 1 axis and this 3 sample axis. So for this kind of method of the rotation matrix, we will need 9 parameters to describe one crystal orientation. Therefore, it's not so straightforward and it's not easy to understand and write or calculate. Therefore, we will have other kinds of methods to represent this crystal orientation. The first one is the Miller index method. I think you already learned what is Miller index during a lecture. And here, we will combine the both crystal plane Miller index and crystal direction Miller index. So it is only right in this format. HKR is the normal direction to HKR is parallel with your sample ND direction. And the UAW, the crystal direction UAW will parallel to your rolling direction of your sample coordinator. There is an example for it. The first one is for this kind of cube orientation. You can see this cube is just like stay there as its coordinator is totally the same as your sample coordinator. Therefore, according to this definition, the normal direction to HKR parallel to ND. So you found ND is here, and this is also the direction parallel to ND. Therefore, it responds to this crystal plane. So HKR is 1, 0, 0. Then the UAW parallel to RD means that here is your RD. You can see this orientation, this crystal orientation is parallel to RD. Sorry. It's 0, 0, 1. Therefore, UAW is 0, 0, 1. Another example is about the ghost orientation. The ghost orientation looks like this in crystal system, and this is the sample coordinator. Therefore, again, if we try to find a crystal plane parallel with ND, it is this plane. So the normal direction of 1, 1, 0 is perpendicular to this surface, so it is parallel with ND. HKR is 1, 1, 0. Then for rolling direction here, again, 0, 0, 1 is parallel with this ND, so UAW is 0, 0, 1. It's much easier for to use this definition than the orientation than the rotation matrix. But we also have a relationship or function to explain the relationship between the rotation matrix and this Miller index. Here, you only need to remember that your first column of this rotation matrix responds for your UVW direction. And the third column here is responsible for your HKR crystal plane in your Miller index. Then we will go to the second method, the Euler angle method. In this way, you will only need 3 parameters to describe your crystal orientation. And the Euler angle method is try to rotate your sample coordinator constant with your or assistant with your crystal coordinator. There will be different kinds of ways you can rotate it. So we will follow a common rule for it. This is named as the Banks method. Then in this method, there are 3 steps of rotation. For each step, you will get 1 rotation angle. The first step here is try to rotate around your initial ND axis and to rotate your initial RD on your 001 crystal plane. That means the plane also obtains the 100 and 010 axis. So your rotation around ND for phi 1 and rotate to move this RD to a new RD position here. You can see this line is already on this 001 crystal plane. Then the second step is rotation around this new RD for a capital phi angle. This is used to rotate this ND to the position of 001. So after this capital phi rotation, you will find your ND is overlapping with this 001 axis. And at the same time, your TD will also move to this 001 crystal plane. It properly in this position. Then the third step is rotation around this 001 axis, and actually it's your new ND axis. Rotation is around the phi 2 angle. Then this phi 2 angle will bring your RD finally to your 100 axis, and at the same time, your TD will be here on the 010 axis. This is because all these coordinate system are the orthogonal system. So maybe it's not easy to understand for the first time. We will also see a simple example here. This is again for the Gauss orientation. You can see the crystal coordinate like this and the sample coordinate like this. So now we need to rotate the sample coordinator constant with this crystal coordinator by these steps. So the first one is we need to rotation around ND, this initial ND, and try to rotate your RD on your 001 plane. But here you can see that your RD is already on your 001 plane because the RD is parallel to this direction, like this line, and this line is already on the 001 plane here. So the first phi 1 angle is 0. Then the second step is to rotation around your new RD. In this case, it's still the initial RD, and try to move your ND overlapping with your crystal direction 001. We can see here, ND is like this, and 001 is like this. There is the misorientation angle between them. It's actually 45 degrees. Therefore, we need to rotation along around RD for 45 degrees. Then you will get your new ND like this. So for capital phi, it's 45 degrees. Then for the third step, we need to rotation along around this new ND and also your crystal axis 001 to make your RD overlapping with 100 and also your ND overlapping with 010. And here we can see for this case again, we don't need to rotate it anymore. It's already there for this crystal orientation. Therefore, the phi 2 is 0 degree. That's all for the Euler angle definition and rotation methods. You can also try it by yourself for other orientations. And here we can also have the relationship between the rotation matrix and these Euler angles. You can see it's quite a complex function here, but you don't need to remember it because we will have a software solution can calculate this relationship automatically. Then we can move to a third method, the rotation axis and angle method, UVW and theta. Here it is defined by, for example, this crystal orientation of this crystal system. You can rotate it around a common axis with the rotation angle theta. Then it will become another coordinate system. So this is a relationship between the rotation axis angle methods and the rotation matrix G. And you also don't need to remember it. And what you should know that this rotation method is not it's normally not used for a single crystal orientation description. It is normally used to compare the orientation between these two crystals. So we will find that it is normally used for the misorientation description. Misorientation is a rotation matrix to transfer the first crystal orientation or crystal frame for grain 1 into the second crystal frame, C2 of grain 2. It is similar to the rotation matrix. The format of it is totally the same with the rotation matrix J. The important thing that here we need to know the common axis between them is the misorientation. The common axis between them is the misorientation axis, and the theta is rotation angle is also defined as the misorientation angle. It is normally used for define your grain boundaries. And this is what you have already learned during lecture, the grain boundaries. So here I just want to mention that there are two kinds of grain boundaries. A definition between them or different between them is the misorientation angle. If you have a misorientation angle larger than 15.5 degrees, it is defined as this high angle grain boundary. And if you have a rotation angle smaller than 15.5 degrees, it is defined as low angle grain boundary. And during the measurement of any point definition, you can see if you have a measured point or you have a crystal point like here, this one point have one crystal orientation. You need to compare the misorientation between each of them or each neighbor pairs. Then if this misorientation between them is smaller than 15.5 degrees, normally we think that they are within one grain. And if the misorientation between them is larger than 15 degrees, we are distinguish them as different grains. So you can define your grain boundary like this. So as you already know about the crystal orientation, now we can see kind of distribution of them. You will have some kinds of materials like this. Within this material, there are random ranged crystal orientations. And in the microscopic level, you will see that their electron or other physical or chemical properties is non-orientated. So it is a kind of isotropic material. But for another case, you will have this higher orientated grain arrangement. Then in the microscopic level, your properties will also orientation dependent. So it is the anisotropic behavior. So in the isotropic materials, the crystal orientation is always random. And in the anisotropic materials, you always have a preferred crystal orientation distribution that is named as texture. I think you will be familiar with this term later in our following lectures. Then after we have defined the grains, we can analyze the grain size. For example, this is a conventional method for measure and calculate your average grain size. If you have a grain size grain distribution map like this, it may be from LOM or SEM. This is just a schematic drawing, and you can draw some equal parallel lines like this, and you can count for the interceptors of this between these lines and the green boundaries. Then you can count for the total number of these interceptors and divide by the total line length, because you have a line scalar like this. Then you can have your average grain size. But this way is not so occurrent, so we will have a more current way to define the grain size. Here, if you have a grain area like this, it will be one part from here. Then you need to fit this area to a cycle that have a equivalent area with your grain. So this is called the equivalent cycle of your grain. Then you will have a the diameter of the cycle is named as the grain equivalent diameter. It is one response for present for your grain size. This grain size is normally follow a log-normal distribution. So we can fix this grain size distribution with the log-normal function, and then we can get the distribution parameters like mu and sigma. Then we can also calculate the mean value according to this function, and this is named for the average grain diameter or average grain size. It is similar for the grain shape. As normally we need to fit a ellipse for this grain shape, so it is equivalent ellipse which have also the equivalent area with your grain. Then we will have two kinds of parameters to describe this grain shape. The first one is the grain shape factor. It is defined as the equivalent grain aspect ratio. So it is calculated by the length of your minor axis divided by your length of major axis. Actually, you can also define it in a inversely way. So you can use the major axis divided by your minor axis. But before you use it, you need to know that your which is your definition. And here we normally choose this the first method. So therefore, the range of the aspect ratio is from 0 to 1. If it is 1 by 1, then it refers to the equal axis grains. And if we have a 1 by like 0.0, it is referred to a quadrilled grains or extremely elongated grains. The second parameter is the grain shape angle or grain shape orientation theta. This is the angle between the your major axis and the horizontal direction. Here we can see a kind of distribution of these two. For the first one, we also need to have a mathematical description of it. But in this case, normally we use the beta distribution to fit this a beta function to fit this distribution, and the parameter here is alpha and beta. We can also calculate the mean value for this grain shape factor as the average grain shape factor or grain aspect ratio. And then for this angle distribution, normally we don't need to fit them or give a totally general mathematical description of it. The important thing is that you need to know which is your most frequency orientation angle. For example, in this case, it is around 90 degrees. That means your grain is tend to elongate along this direction. It is perpendicular to your horizontal direction. This is maybe your rolling direction for this case. Then we can go on for the second part, the software introduction. The first software is ImageJ. Is what I want to show you here. It is a simple and powerful method to analyze your LOM and SEM figures. For example, for this one, these are some particles among this matrix. Then you can change your construct to pick up these particles like this, and also you can fit them like with this lips. But we can see that for most cases it works good, but for this one, it mixes up these two particles. In this way, you can also try to calculate your error of these particles and also calculate the final error fraction of these ones. And here is another example for ImageJ. This is one of my material is a dual phase steel. So in this material, you have two kinds of phase. The first one is this one. Under SEM, you will see a uniform or relative uniform black area like this, and another phase is like this. Under this phase, you will see some structures like this white lines and within it. Therefore, you can mark these two phases with different colors, and this software will give you a final fraction of these two range. For example, for this case, we have a yellow phase a little larger than 20%, and blue phase is a little smaller than 18%. But you need to notice that if this is the same sample and same material, but we move to another measurement area, we have seen that the blue phase is increased to around 60%. 60%. That means the LOM or SEM observation, or even much smaller observation like TM, they only have a limited method area. If you want to obtain this global overview microstructure description of your material, you need to repeat your measurement within a large sample surface area with at different positions. Then you can obtain the a systematical or schematic no. I forgot that word, sorry. Overall description of your material microstructure information. Then we will go to the second software. This is also the main point of today's exercise, the Mtex toolbox. It is normally used to analyze the EBSD or XRD data. And here we only focus on the EBSD data part. As you already see, this kind of crystal orientation map. For each grain, you will have one orientation, and they will be different with each other. And you can see the pixels here is response to one method point. On each method point, you can obtain this kind of dates. It's a serial state, obtain a lot of information here. And if you do this measurement, or if you have a different EBSD measurement system or detector produced by different companies, or if you set with a different date format as the output, you will get this different kinds of output dates. They will be a different format. For example, this ANJ type date file normally comes from this ORM system, and the CTF date file is normally comes from the HKR system from Oxford company. But actually, these dates are only in different format, but they could contain this same information you need. So the first basic information you need is first this 3 Euler angle, then followed with the X and Y coordinates. So that means for this method point, the 3 Euler angle is like this, and its coordinator is like this. And in your CTF file, you will also have this Euler 1 to Euler 3 and XY date. And you can also choose your output is in radian or in degrees. Then you can also obtain this kind of grain ID and the phase type. So it is dependent on your crystal structure during measurement. And one more thing is you can get this kind of parameter to describe the quality of your Kikuchi pattern. So for they are like the image quality and band construct parameter. This IQ is from the ORM system, and BC is from the HKR, the second system. But they are only depend on their difference between them is only depend on different kinds of calculation method. But they have the same physical meaning. That means the intensity of your Kikuchi pattern. And like how strong it is. And then it's the confidence index, CI, and mean angular deviation, MAD. These two parameters also come from the two different systems, but they have a same physical mean. That means the occurrence of your calibrated K-cushion pattern. That means to what content you can believe this K-cushion pattern, and how the which can like whether this data is reliable or not. So this is important for your post-date progress. So you need to delete the date which is not so reliable. And now we will start with the software part. So again, I think all of you should already download this this toolbox and also copy it to your MATLAB work folder, and also you need to download this EBSD input date. So could you give me a response by Zoom, like click the yes or no button, then I will know your progress with this. No response? So have you already finished the download of this file and also the date file? If no, please do it right now, because we will need it for the following sections. I think we still have 1 hour, or yeah, we still have 1 hour left. So if you have MATLAB on your own computer, that's much easier. You just need to download this MATLAB toolbox and copy it to your MATLAB folder. If you don't have MATLAB on your own computer, you need to go to the Auto VDI system with this one, and just make sure that every time after you using your VDI system, please use this sign out button, not just the disconnection or close your window. This is helpful to improve the VDI system performance to make it faster. So for download Mtex, you need to go to this website and choose the newest version here. If you have already finished the download, please tap your yes button. Then it will show near to your name. Then I can review it. It is important for today's exercise and also for your task 4 for this week's assignment. If you already finished the download and copy it to your MATLAB folder, you'll need to extract it. Just find this download zip file and double click it to extract. Then you will find a folder like this. Then you can double click it or right click and add to paths to make sure that this folder is under your MATLAB work path. If there is no reaction, I will just go on. I hope you can follow this progress.
I have a question about that zip file. So I have the zip file now in my MATLAB folder, but when I double click it, it doesn't make a new folder. It just stays as a zip folder, and it doesn't show it like in the right side of the MATLAB folder in the top, what do you call that, working directory?
No, if you have this one, I think it's better show you on my own computer.
I just tried to do it again, so I will see if it works.
You need to wait for a while. It will take some time to extract by MATLAB.
I think that file might be quite large, so my computer is struggling a bit to. I don't know if it's just haven't like finished doing the task or what.
So that's the reason why I asked to do it before the exercise. Yeah. So here is your zip file. Normally you double click it and it will extract by itself. Then you will go through this folder. You will say it's already, maybe it's already there.
So there should be like a zip file and then a folder down below.
Yeah, then you need to double click this folder, or yeah, for me it's already there. So or you just right click and add it to path.
Yeah.
Then you also double click to enter it or open it. There's also one more. Then under this folder, after you have extracted everything, you can find this startup function. Yes, you need to extract it. Sorry.
Yeah, I think now there seems to be a difference. There's like a whole lot of folders under the Mtex 5.4.0 folder, but it's like light gray, so I think it just isn't ready yet.
Yeah, you can also check in your folder in your folder window. Then if you open it, it looks like this.
Yeah. Yeah, I can see that stuff like here in the method.
200 something.
Yeah, but it's my computer is trying its best to do this task, so.
Oh, it's quite a large. Yeah, like this. Then after you finish the extract, please right click this startup function and click run. Then you will see if you see a window like this, or if you see that the initialize Mtex done, that means you have already successfully installed it. So could anybody type like yes to tell me whether you have finished this installation? I have to mention that for every week's exercise, we need to learn one software or at least one software. So the software information actually has already listed on my courses. You can see them, I think, on the home page, like here. And we also linked them on the first introduction lecture slides. And for every week, I will add the how to install and how to download and the first initialize or installation of the software for Friday's exercise and your assignment on the second lecture slides on Tuesday. So please finish it before this exercise session starts. Yeah, the exercise session will start at 10 o'clock every Friday morning. It's not opening the startup, you need to run it. So you right click the startup and run. If you have already opened it like this, you can also click run here. After you have run the setup, you should already see this sentence and this part. So that means you have already successfully installed it. And I think all you should already familiar with the MATLAB window or MATLAB layout. So if you need to type your comments in the comment window, I will show the comments required later. Then the generated date will show in this workspace window. You will also check your comments in this comment history window. And after you have opened some script, they will show in this editor window here. Because we have limited time, so I hope every one of you should already finish the installation, and we will go on for details now. And if you haven't finished it and can't follow it for the first part, maybe as I have already write a detailed steps in this slides, so you can follow the slides later. So let's go on for the first part. How to define your crystal orientation in Mtex. First, you need to, I'm not sure whether you can see my screen with this script now, or should I zoom in them? How to do it? No, I think MATLAB don't have this function to change the font size. Okay, I can type in something here. First, before we need to define the crystal orientation, you need to know that always your crystal orientation is related to your crystal structure. So you need to define your crystal structure first. This is the default comments for how to define a cube crystal structure. So the first one, you need to type in the crystal symmetry. It's equal to your CS. It's equal to crystal symmetry, capital S here. Then we will give a cube crystal symmetry like M-3M. Just remember it, please. If you want to know more about the crystal structure or crystal symmetry, you need to attend some advanced course for material science and engineering. So this one is for crystal symmetry definition. Then we will also meet the sample symmetry definition, like the SS for sample symmetry. And for a cube, we use MMM. So after these two definitions, you can define your crystal orientation now. And there are two ways, or actually there are several ways can define the crystal orientation. But here we will learn two ways. The first one is by Euler. That means use the Euler angle format. The second one is by Miller. That means use the Miller index format. We will try the first one. For example, the Gauss orientation. If you still remember that your Gauss orientation, here, first by Euler angle, the Gauss orientation is 0, 45, and 0 degrees. Then we type in orientation Gauss. The first by Euler is equal to orientation point by Euler, capital E. Then you just type in your orientation here. But remember that in MATLAB, the default unit system is always in radian. So if you want to use degree, for 0 is okay, but you for other values you need to add a type degree. Like 45, you must add this one, then 0. And this crystal orientation is under the crystal structure system as we just defined this CS and SS system. So add this CS and SS, then enter. You can see that orientation is defined here, and it also show your work Euler angles like 0, 45, 0. Then we can use the second method to define it. It is by Miller method. For Gauss 2 is equal to orientation point by Miller, capital M. And this for this Gauss direction, I can show you Miller index here. So for H care, you need to write H care first, like 0, 1, 1, and then followed with UVW. Here, your definition is a crystal plane or crystal orientation by Miller index, but it's always written in this vector format. So you need to use this. You need to use this kind of the breaks to define your vector. So for UVW, it's 1, 0, 0. And again, you need to define it under your crystal structure system. So add CS and SS followed. Then tap enter. Again, you can see that this orientation can be defined by Miller index, and it also shows the same Euler angle as what we defined before. So 0, 45, 0. Then we can plot these two to see whether they are totally the same. For plotting, using a figure window first, then, oh, sorry, I forgot one thing. For plotting a crystal or plotting this kind of cube, you need to define your cube shape first. Use this command. CS is not the same CS as before, so you need to change one your capital or change another name for it. But this CS is responsible for your crystal shape. So it looks like this one. You need to type in crystal shape. And here we will use a cube crystal shape. Sorry, cube. Then you need to define this cube crystal shape again under your crystal system. So just add CS here you will see this. Oh, sorry, I type in shape. I forgot one E.
Hi, Wenqi. Someone asked that the commands for the crystal orientation cannot be copied from the lecture slides.
You can't copy it. You need to type in by yourself, please. And now you can see this crystal shape. It's for a cube shape, so you have 6 faces and 8 axes here. Then we need to do the figure plotting for this rotated cube. Build a figure window, then use plot comments. And here we need to define first where we would like to plot this cube. Like we use the zero position. Then plus the orientation you want to plot, like for goals 1. And you need to type it with what you have already defined, the crystal shape. I think I typed in something wrong. Sorry. Let's check it. It should be right. I forgot something. Let's try directly plot it. No. As I just installed it the day before yesterday, so maybe I need to restart it again. Okay. Oh. Yeah, now it works. So it's just some problem with my setup for Mtex. So here you can see the first figure for the first goals orientation definition. And here it's harder to really observe it without any vector definition here. So we just use the axis on to investigation the outline the sample system. Then you can see it looks like this. And now we can also check for the sector and the identification or the second definition for this goals orientation. Again, we plot it at 0, 0 point plus orientation goes 2 is defined by your Miller index. Oh, I do a wrong type. So it's times, not plus. So you can compare these two. The first one defined by the Euler angle method, then the third one defined by this Miller index method. We can also open the axis. Okay, let's do it in this way. This one and this one, they are totally the same for Miller for Euler angle definition and with the Miller definition. So this is for gauge orientation. And as I said, we can also calculate the geometry matrix by this software. So it's easy to obtain this geometry matrix, like your geometry matrix for gauge. The first one is equal to your okay. Professor just asked me to become slower. I need to say your chat channel. Where's chat? Okay, I just would like to ask, have you already followed this definition about the orientations? No answer. If there is no answer, I will think that all of you have already followed this. Okay, one yes. Yeah, because I think some of you have already finished the software download and the installation before this exercise, so I think they can follow well. So actually, all these comments has already in your slide, in the slides. So you can also try to do the practice after this exercise section. And here, I just want to explain them as much as possible and try to make most of you can understand this workflow. For details on your comments, you can check it later. Okay. After we have defined this orientation and also plot them like this, I'll close these two round windows. So this is both for gauge, and we can show the rotation matrix of this orientation. So it is typed in like orientation gauge. So type in the orientation which you would like to see and point matrix, and here in Mtex, the matrix definition is a little different with the general definition of rotation matrix. So it is the transpose of it. So you need to add a quarter after this. Then you will see, type in enter, you will see something like this. This is your gauge orientation. And the rotation matrix for this gauss orientation, you can see the first column is for UVW, it's 1, 0, 0. And the second, the third column is for the HKR, it's 0, 0.7071, 0.7071. And after normalization, it is 0, 1, 1 for your gauss orientation HKR mirror index. And we can also do the same thing for the second type defined gauss orientation. It is directly defined by your mirror index. Then you can see they are totally the same result. Here, yeah, it's also 1, 0, 0 and 0, 1, 1 of the normalization for HKL. So this is comments for how you can obtain your rotation matrix by of your orientation already defined here. Then this is the basic thing for how to define your orientation and how to do the converting between the rotation matrix and your mirror index and the Euler angle. Actually, if you just type here or click this orientation, you can see it already store a lot of images here. My computer is also slow. It's actually, the MATLAB is slow. You can see this phi 1, capital phi, phi 2 is already there, but they are right in radian, it's not in degree. And also the crystal structure for this orientation is here. And this is another kind of orientation represent way. It's for a vector way. So you have 4 vectors. And this 4 vectors is a key point to calculate the Gauss, the J matrix and also the mirror index. If you are interested in it, you can just search for a Mtex documentation for further information. We will not use them here now. And then we can define the secondary orientation like for cube. For cube, we can also define it by Euler or mirror index. The simple one is Euler. And I can already tell you the Euler angle for this cube orientation is 90 degree, 0, and 0. So let's define the orientation cube. Orientation point by Euler, capital E. Then type in your orientation here, 19 degree, 0, 0. And then under the crystal structure, CS and SS, enter. You can see this orientation here, 19, 0, 0. We can also plot it. You can search for these comments before. If you have already typed in something like this, you can just use the search function to do it. So we can plot the cube orientation like this. You can see it's here. And this is a cube. And this is what we defined before it goes. Now we can calculate the misorientation between these 2 orientations. The first one is to calculate the misorientation axis. The commas are here. The first one is for axis common between these 2 orientations. The second one is for angle between these 2 orientations. So let's try the common axis UVW is equal to axis between orientation. You can choose either the first or second Gauss you defined before, and between this cube orientation, enter. Then you can see the common axis here is 1, 0, 0. Then we can check for the misorientation angle theta. It's equal to angle between these 2 orientation Gauss 1 and orientation cube. And here, if you just type in this way, you will show this in radio unit. So we need to divide by degree to convert it to in degree. So you will see 45. That means if you rotate, this one, if you rotate it 45 degrees, there will be a same crystal orientation. Can also show your result here. So after you type in this axis and angle common, you can get the result like this. So this is a common rotation axis and this is a rotation angle. This also means the misorientation degree between these two is 45 degrees. So I would like to ask again, have you already finished this part? Your name is so long, Oscar Hawken. You're always the first one. Sorry for my pronunciation, maybe it's not wrong. Yeah, really. See me. And if you have already finished this one, we can start the EBSD part. If you still questions with this one, please raise your hand or type in chat. No? Then we will start the second part. It's meant about the EBSD data analysis. So the first part is only tell you something about the crystal orientation operation in Mtex. And then it's really do something with your EBSD. So here, if you still have this, if you go up in this window, you can see something here. After you install your Mtex, it will show like this. You can directly click this import EBSD date. Then it will show you one window like this, import window. And if you already lost this one, or if you just already clean your window like this, you need to type in a command here to open this window. Like import under short underline, where's short underline? Okay. With. So it will also show. This is your import window, but you need to click this EBSD tab, the second one. This perfect tab is used for a import date from XRD, but we will not use it today. So you just type this EBSD. And then you need to click this plus to add your EBSD file. And I have so many files here, but I think for you, you just try to find them when you have already, you just download from my courses. It's EBSD date CTF file, and choose it. Click open. Wait for a while. It will show here. So please let me know after you finish this step. Great. Okay, this is only the first step for import. Actually, we need to do some settings update. So after you already show this, you already choose this CTF date file here, you click next. Then this is the first setting for your faces. Actually, if you see the, show you again the axis size, after you chosen this date file, add it to this import window and click next, you will see a lot of face settings followed it. So this is a different face parameter or settings shown in the according to their method date. And this is important, but as if you believe that your EBSD measurement process is right, you shouldn't change anything here. So these dates are directly from your EBSD measurement process. So like here, the first phase is generally the non-indexed point. As we have explained before, for Kikuchian pattern, it is measured point by point. For some points, if your lattice distortion is so large, like in the green boundary area, it can be indexed with one crystal orientation. So it will be marked as the non-indexed point. So for phase 0, it's non-indexed. Then you will also see another phase if you click next. So like for this sample or for this date, it have phase 1, 2, 5. So for phase 1 is a kind of aluminum alloy, but here is some basic information for this this kind of alloy crystal structure. So the point group is blah, 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 the axis lines angle is what, and please don't change it because this is directly from your EBSD measurement. If you do it right in a right way during your measurement, you shouldn't change it here. So just believe in your date. Then for phase 2, the same. The next phase 3, next phase 4, and next phase 5. So that's all. Please don't change it. And all these points are index points. So just EBSD, just index them and mark them and identify them as this phase with this structure. So don't change it. Just click next. Then you will see this kind of specimen reference frame. So this is also what directly from your EBSD measurement. If you put your sample rightly and when you do the EBSD, so you just use the default setting, do not change them. So here you also click next. Then you will be the final step for this import process. So you will see the summary of EBSD date. We will have around 22,000 orientations or points are non-indexed. But meanwhile, we also have this more than 400 points are indexed and marked as this anomial phase. And here we the EBSD system has this kind of phases, but actually in this state, we don't have this kind of phases. And here, choose the import to a script, a MATLAB M file, and click finish. Then you will see this kind of script for import. So I hope you're already in this stage now. And here in this script, you need to save it first and click run. If you don't want to save it as a file, you just copy this things to your main comment window and enter. Then it will do the import system by itself. Just wait. So it's running now. You can see this one. It's extract the eBSD date. It's still running. And after running, you will see that here is a new date structure here. It's eBSD structure date. And here is totally eBSD method point. On my computer, the import process already finished. I think maybe some of you is still doing it. So I will explain shortly about this generated script. So the first part is what we have already explained. It's the default setting from the eBSD measurement about the different crystal structures of your method faces, and also the specimen structures or specimen coordinators also according to your measurement. And here is you can change the work path or work direction of your MATLAB or import date file position and path and name. Then the last comment is really how to load this eBSD. So if you have seen this eBSD with these points here, that means you have already successfully imported this eBSD date. So have you finished this step already? Okay, great. Then we need to do step by step to analyze this eBSD date. So this is default setting for face. I have explained the default setting for crystal, and also this is how to save it and how to run this import system. Then after running, okay, this is the structure of the script. After running, the first thing that is we can plot this eBSD date and to see the basic face. If you directly do plot, I think I need to open a new figure window. Please always open a new figure window before you plot something. So plot eBSD. And here I prefer to add coordinator on. Then you can see the method area of your eBSD date. I hope my spell is right. Okay. Tap enter. Then you can see this face. I'll try to show you the comments here. Okay, great. And in this way, you can see that in this eBSD date, we have the first non-index points. They are shown in this white, and you can see most of them are placed or looked at this some boundary areas. And this is because the sample preparation is grinding lines. Because the grinding also introduce a large lattice distortion on your structure, on your material, so it will also show as a non-index points. Then the focused face here is aluminum. It's showing in this color, this dark blue color, and the master area is up to a little larger than 800 micrometer times by little around 600 micrometer. So this is the whole method area. Okay, then we will go on with this plotting the eBSD orientation map. So you need to first generate the color coding for this eBSD orientation map. So the comments is here. It's just type in the EPF key I will explain later what's this. So the IPF color K. Be careful, it's this type.
Hey, can I ask you something quickly?
Yeah.
Yeah, so I tried to do that figure plot, and then there's instead EBSD.
It's plot EBSD, and if you also add this coordinator on, it will show your coordinator on your figure. If you didn't add this coordinator on, it will only show this map.
Okay, because it tells me that there's undefined function or variable EBSB.
Then it's because maybe you haven't finished this load process. So after finish, you will see this EBSD variable here. So if you haven't import it, you will confound it.
Okay.
Okay. Yeah.
Yeah, I can see it in the workspace.
That's great. Then you can try the plot again. And for those who have already finished the import and also the plotting for face map, you can go on try to type these comments to plot your orientation map. And the most important thing is that the orientation map is only used for single face. So for everything you plot a orientation or you calculate orientation for grants, you need to point out that this is for a anomial face. It's focused single face here is anomial. So we need to add a EBSD for only for this anomial face. INIUM. Then it will generate a IPF color coding for this face. Then you also need to point out which vector or which direction you want to do this color coding. So it is inverse Hall figure direction. It's equal to vector 3D, sorry, small 3D. And here, normally we use the Z direction for the inverse Paul figure direction. This is explained by this one. So this is a color coding for this, what you have defined by this IPF case. And here the Z direction for this measurement is ND, because this measurement is done by your RD and TD directions on your RD and TD plans. So that means the Z direction is ND. And this color coding means that if you have a color in red, so your sample ND is parallel with your crystal 001 direction. And if you have a color in green, then it means your crystal 101 direction is parallel with your sample ND. So this is the meaning and why we need to define these two color, the color coding case first. Then we can plot this color coding. Here, you can first define your colors in this way, and you can also directly use your colors here. We choose the first way. We define this color using this color coding K. Yeah, color coding K. we use the orientation to color. And also we point or identify that this should be for EBSD aluminum phase. And orientation. So we use these orientations as we use the orientations in this EBSD single phase and transfer or convert it to color. Use this color coding. Yeah, you can see that it is working for all these orientations here. Then we open a new figure window and plot this orientation map. Again, this is only for this phase aluminum. Then use these colors as coding. Sorry, there's no S because when I type it before, I only use color. So use a variable you defined before. Now you can see this is the EBSD orientation map like this. So have you finished this step? I can show you comments in this way.
Sorry, can you show this color command one more time?
Here, you can see here on the screen.
Yes, but can you show in your code? It's easier to understand then.
Because I forgot to add the comment afterwards, so it shows all the results here.
That's a long list.
Yeah, okay, it's already, and maybe you can see here. These 3 lines for coding, and this is for figure and plotting.
Yeah, sure. Thank you.
You're welcome. It's too long. So this is the orientation map. So after you finish this orientation map plotting, as we also explained before, we need to calculate or reconstruct grains according to this orientation map. For each point, if you just try to zoom in one point, maybe. Okay, if you zoom in this map, you can see this pixels here is the measured point by point. Then you need to calculate the misorientation between each point. You will also see this the white color here is for the non-indexed points, and all the colored points are the indexed points. They have already their own orientation. Then you need to calculate like this the orientation between this point and this point to calculate the misorientation, whether and try to figure out whether it's larger than 15 degrees or smaller than 8. If it's larger than 15 degrees, like this one, maybe it will distinguish this as a grain boundary. And if it's smaller, maybe like this two, or within this area, it will identify as a constant grain area. So after you plot this orientation map, we will do the grain reconstruction. And before we do the grain reconstruction, we need to make sure that all the data points we used here are reliable. So first, we need to figure out that how the confidence index or the occurrence of your calibrate Kikuchi pattern or your calibrate crystal orientation. There we use this criterion for it. We only use for the CTF system or data format. We only use the data point with MAD smaller than 1. That means this method data have a higher occurrence or it's more reliable date. So pick up this date. Then you also need to delete all. Sorry. Is there any questions? No. Okay. Then the second step, that you need to pick up this indexed points. So delete all the non-indexed one. So just go to these two columns and finally get your EBSD date as this. If we do it step by step, the first one, EBSD, correct. That's equal to EBSD date with MAD smaller than 1. Then you will see the initial EBS date is up to 461,000 points. And after this pickup with reliable date is reduced to, oh no, this is a common one. So they reduced to the 459,000, almost less than 1,000 difference. And then we need to pick up here. The first non-indexed point will be deleted. So we only focus on this one. So we will pick up this 95% dates here. So the final EBSD correction identified date is equal to, again, EBSD corrected date with the indexed points. If you have a single phase, you can also type in your phase like EBS index aluminum because they are the same. The index point here as a single phase is also aluminum phase. Then you will get these points. It's totally same with the aluminum points here. So we will use this EBSD database, the EBSD correction index points for grain reconstruction. Then you will see here, this is the criterion for distinguish different grains. So it's the misorientation angle larger than or at least the misorientation angle is 15 degrees. So you need to reconstruct your grain structure with this common. So calculate grains common or function. It will return first the calculated grains, then the grains ID and the mean orientation to your each EBSD date. So it will return first the grain structure, then grain ID on each EBSD date, and also the this means to mean, it means a mean grain orientation to the EBSD date. I will explain it later on figure what is mean grain orientation. Calculate grains with EBSD correction because here when I do it, I type it wrong. So I need to use the term I identified, a variation number I identified here. The angle, the entry will be 15 degree. Oh, okay. I make a mistake because there is no this variable. I didn't define it, but it done with it. Strange. CORRI. We'll do the reconstruction with the right names again. But you see it already works even with a different name. It will generate a new EBSD for it. Now everything should be right. Then the if you see here, for example, like this area, maybe it can be identified with one grain, but we can still see some grain orientation gradient within this grain. Therefore, it will calculate like this for this grain, the mean orientation for all the points in this grain, then give it back to EBSD. So that's why you have this EBSD correlation that misorientation to mean. After we do the grain construction, we can check how many grains we have. Actually, it's just the length of the grains. So you can directly see it here, actually. It's 5,586 grains already. Number is equal to length grains. It's this number. Then we can plot this grain mean orientation figure. I just noticed that it's already 12. I don't know whether you still have courses or what. Yeah, it should be end at 12, but you should know that we start 15 minutes later today, this morning. So if you have other courses, I'm afraid you have to go. And but this is important for your task 4 assignment. So maybe you can follow all the introductions here with comments and how you can do with grain orientation, how you can do with post process on your grains, and how you can pick up all your grain date and do the curve fitting later. Or if you don't have other courses and you want to stay here, I will finish this session. So after you have already constructed all your initial grains and get this number, you need to notice that we will have some data points. It's with a quite small grains, maybe like this area, or it will have like this. There's only one point. It seems it's different with all its surrounding points. Yeah, so do you have any questions? Okay, so like this one, it may be a distinguished by some system error or by your EBSD during you do the measurement. Therefore, we need to also delete these very small grains. Normally, we use a grain size smaller than 2 as a criterion to delete these very small grains. This means if you have a green only contain 2 method points or less than 2 method points, they will be deleted. So we will do the delete again. Here, that's correction. Greens, if the greens have a green size, capital S, smaller than 2, it will be deleted, marked as empty in MATLAB is delete. So you will see the number here is further reduced. And then after this deletion, we need to do the grid reconstruction on this EBSD date again. You can just use the common you tapped before for this one, but remember, yeah, okay, you don't need to change anything because they have, you just delete it in this EBSD, so you just use it again to calculate, to recalculate your greens. So do the green calculation again. Then again, we can check how many greens we have now. So after deletion, you can see the greens number is reduced to reduced by around 200 greens here. Then we can pick up the greens with the focus face. Actually here, the focus face is only the single face, so you can also you can also just leave it as greens. They should be the totally same with this one. We can test it again. Greens aluminum is equal to greens only with aluminum face. It's the same green number as you have already after deletion. So the total green number for aluminum phase is the length of this one, of this variable, greens aluminum. It's 5,350. Then you can plot again a green orientation map. This one is not using scatter orientation, but the mean orientation instead. Generate a new finger window, then plot these greens. So with your green aluminum mean orientation as orientation color. Oh, I forgot one S. I think it will be an error. Yeah. Greens aluminum. Close some windows. It's still running. Here, if you compare it with your initial orientation map, we can still zoom in this part. My meta will also become slowly. You can see the black lines here is green boundary. You already show the green boundary. You can already see green boundary here. And if you focus in one green area, oh, it works now. You can see this region is this region, this region is this region. So for these two, they are not belong to one grain. It's distinguished as two grains. But for this one, these two, you see it's as maybe different color, but actually their misorientation is within 15 degrees, so they are distinguished as one grain. And the color is shown as the mean orientation of these parts. So that's what its grain mean orientation means. So this color mapping is for grain mean orientation map. So that is all from the grain reconstruction and also the grain date or the post-process for delete some non-reliable dates or delete some error dates. Then you will check for how many grains you can obtain and also plot the grain mean orientation map. So this is a comparison between your grain mean orientation map and the EBSD scatter map. Then after we have already done this kind of grain reconstruction, we can analyze this grain map, grain date. But before, we need to notice that for grain size and shape analysis, if you focus on some boundary grains here, they are not the whole grain actually. So it's just because your measured area is stopped here along these lines. It not means this is a whole grain for this one, like for example. So we need to delete all the boundary grains for the grain size and shape analysis. Then you need to follow this kind of structure comments to delete this all boundary grains. Think because of the time limitation, I will not do it step by step, but you can follow the structures here. The first one is you need to pick up all the boundary grain ID, then give this ID to a grain ID term. Then if the grain ID is equal to 0, that means this is boundary grain, then you just delete these boundary grains. Then you can also plot this with this boundary grains. You will get this figure. You can see all these grains pick up here are the boundary grains. And the left one are the inner grains. So we will only use the date for the inner grains for further grain size and shape analysis. If you go back to these comments, you can also check after you delete all the boundary grains, you will also check how many inner grains you will have. Can run it faster for this one. So you need to pick up the boundary grains and also delete. You can plot them first before you delete them. Then you can delete the boundary grains and plot only the inner grains area. Then we will show the result here. This one closed. If you want to, so you can get these two kind of map, and you can get this inner grain number. It's not finished the process yet. Okay, now it's here. So for after you have deleted the boundary grains, it's around 300. So you will get finally 5,000 grains here for inner grains. Then all your data has received in this grains structure, this one here. If you click it, you will see a grain structure date. Double click to open it. You can see different properties of this grain have already stored inside. Yeah, you can see the grain size here. You can see its face ID. You can see the center position of this grain. You can see the corresponding grain color and which kind of mineral structure or crystal structure it belongs to. And we can see also here the mean orientation. This is a orientation structure date. And this is for which whether it's inside on the boundary or not. And now we can try to extract some dates like grain size for this grain. But here the grain size is for how many method points within this grain. It's not directly how long is the diameter or not. So you need to use some comments to extract how the equivalent diameter, like this one. This one is for equivalent radius, type by 2 is equivalent diameter, and here this one is for the grain area. So how large is this grain? If you type like a grain size, it is for how many points in this grain. And this one is for the aspect ratio. But in Mtex, the aspect ratio is not as what we defined for mineral axis divided by major. It is used for major divided by mineral. So we need to divide it by 1. So 1 divided by this aspect ratio to transfer it to mineral axis divided by major axis. Then you will get this dates. I can show you one for grain. For grain D, for grain diameter. For example, the grain equivalent diameter is equal to the grain equivalent radius. So the grain equivalent radius is as grain equal to length radius, then times by 2. Then you will get this grain equivalent diameters for all these more than 5,000 grains here. The result is also shown on my screen. And we can also get the grain aspect ratio equal to 1 divided by grain aspect ratio defined in Mtex. Yeah, it is also for more than this 5,000 grains. Yeah, it's showing here. And for the grain rotation angle, the fitting angle, you need to fit the E-place first, the equivalent E-place. So you will meet this common to do the fitting first. You can also plot it with this fitting. And then you can get the first term is for the grain shape angle. And you can also get this long axis and the short axis. Actually, they are the vectors in MATLAB database. So I will not show this part anymore. You can practice it by yourself later. Then I can show you, after you have obtained this kind of grain diameter or aspect ratio data, you can do a curve fitting for it. Here in MATLAB, we can do it by first these applications here, the distribution filters. Then you can add your date want to fit it. Like this one, choose your grain diameter date and create this date set. Okay, it's here. Then you need to generate a new fit for it. And for grain diameter, we use log-normal distribution. And just click apply. You will see here it is fitting according to the density. You can also do it fitting according to your CDF, accumulate probability functions. This is not displayed, so it is not controlled. The control function is in this new fitting windows here. I think as you have already have a MATLAB course from maybe your last semester, so you should already familiar with this process. And also, you can also do the function fitting, use MATLAB functions like this one, the fit distribution function. And as this work window, after you check the distribution here, there's no beta distribution. I think there's only gamma distribution. Yeah, I checked last time, there's no beta distribution. So if you want to do your beta distribution fitting for your this green shape date, you'll need to do it by this fit distribution function. So please try to do it by yourself. This will be one task for your assignment. So that's all for the basic operation by Mtex to analyze the microstructure and grain date. And this is resources for today's exercise, including the knowledge from textbooks and also the software introductions. And now, if you still have some questions, please ask now. There is a problem about the recording upload because we didn't find a proper way to upload videos onto my courses. So we tried a lot of methods, but none of them works properly. So is any of you have ideas for the video upload? But I think this slides has already given you all the details, like how to do it. Maybe it's only lost some explanations on the terms.
Can I ask something quickly?
Yeah, please.
Yeah, just to make it clear for myself. So the assignment that's deadline on Sunday is the one that is found from the assignments in my courses,
yeah,
which have for calculations.
Yeah, you have already sent the assignment here. I think you all should belong to this group and you have access to this assignment.
Yeah.
And as I also type in here, this is your task description in PDF, and also the date necessary for task 4 is also attached here.
Okay. So do you need like MATLAB stuff to complete the exercise?
Yeah, for task 4, you need what I have explained. You need Mtex to do it. If you have problem with it, please just write me an email or give me a description on the discussion channel.
Okay.
Yeah. Yeah. For today's exercises, because normally we should start the exercise at 10 o'clock, but today I think most of you think maybe it start at 10:15, so we wait for 15 minutes for you to for everybody is here, then we start already 15 minutes later. And for exercise, because we made the software operation during the exercise, so as I said, you need to install and download all these necessary files and the softwares before the exercise. And today we have to wait most of you to finish the downloading and the installation. So for next time exercise, please do it before the exercise start. Then I think we can finish the exercise within 2 hours. And then we can still have more question times for your questions regarding to a assignment or the exercise content or even the lecture content. But for today, I'm sorry that we are being so late for today's exercise. And for the lecture part, we will also try to improve it from next week. Try to control all the content within I think only less than 2 hours. Yes, yeah, 15 minutes less than 2 hours. And this is because for material science and engineering, we have so many things we would like to share with you. So we already try to control the length of our lecture. I hope you will enjoy it. And for next time, if we still access the time, we will upload the slides with more details to the website. You can go through it after the lecture. I think Professor have something to add.
So Wenqi, yes, I want to just add a few sentences with 2 minutes or so. I mean, thank you for such a comprehensive and interactive exercise. I know you have been preparing this for a really long time. I think for the student, you probably didn't see or probably see, but it is really challenging to offer a online demo with your interactions. So thank you so much. And yes, the time was a little bit over, but I was very pleased with the whole activity. So we will definitely also get the time better controlled. And so if no one has any more questions, I mean, I don't want to really make a long speech and too much noise here, but I just
I got a little question. Can I ask it now?
Okay, go ahead.
So Q&A time is over, as I understand. And if I've got like some problems, should I preferably write email or just leave the message on Q&A forum?
You're more recommended to leave on the Q&A channel if it's about the content, it's about the technical issues. I mean, if it's a personal issue, of course, you don't want to post it there. You can write us emails, yeah? If you're asking something about the menu.
Yes, yeah, I understand. But if Q&A time is on Wednesdays, isn't it?
Yes.
And if I have questions related to this assignment, this week assignment, I do not receive any answers this week, do I?
Actually, because we have opened the assignment on every Monday, so you can check the assignment already before the Q&A time before Wednesday afternoon. Then if you have questions about it, you can already ask it during the Wednesday Q&A time. But for this week, there's only one student to join the Q&A time, so I only answer to him. I think maybe mostly you didn't notice this. So if you still have questions about assignments, you can ask me now or write it in a general discussion channel. Yeah, I'm afraid you have no more Q&A time for this week.
Yes, thank you.
For the current one, I think, Milan, you're also asking if you have problems with this particular task and exercise. Yeah, then you don't have really an interactive chance anymore.
Yeah, if you like for normally we design the assignment task by task related to every week's lectures and the exercise. So the exercise have to wait until Friday. So I will try to control the content among every exercise. So if you have a question about the assignment regarding to this exercise, you need to ask it during the exercise, like now. Yeah.
Okay, I got it. Thank you.
You're welcome.
Good, everyone. So thank you for staying too late with us.
Yeah.
And I hope you gained really some wonderful knowledge using MATLAB and Mtex. I've learned a lot even. Yeah. So thank you, Wenqi. Thank you very much. And so enjoy the rest of the day and the weekend. See you next Monday, guys.
Have a nice weekend. Bye.